All right, so what we're going to be looking at today is how to solve, I mean, technically they're exponential equations, like we're trying to solve for a variable in like an exponent, and we're going to see how we can use logs to help us. If you remember way back before spring break, I think it maybe even was like a week or two before spring break, when we first started chapter 7, we looked at solving equations by using a common base. So like, for example, if you can write both sides as having the same base up to a power, you can just kind of get rid of your bases. So for example, this first one, basically you want to ask yourself, can I write 25 as a base of 5? Well, that would be 5 squared. So now that these have the same bases, you can just get rid of your bases and set your exponents equal to each other. So I don't know how familiar this seems, or hopefully not like too alien. Similar idea with like a question like 2, like even if like there's no way I can really write 27 as a base of 9 at least easily. I mean, you could like fractional exponent that would work, or decimal, but you could write like 9 is 3 squared. So just remember, if you have like binomials in the exponent, you're gonna have to
Flirting? You think I'm flirting with you? I am not flirting with you. No woman.
welcome, Felix. And then like 27 would be 3 to the 3rd power. So then you could just kind of get rid of your bases. I'm going to just go ahead and distribute. So that'd be 2a plus 4. That would be 12a minus 6. Then if you solve this, I'm just going to kind of do this quick. You would add the 6 over, so you'd have 10, and you'd subtract the 2 over, you get 10a. So you get a is 1. I know I kind of like skipped right in some steps, but this was how we would solve these, by using a common base. But the problem with this method is it only works in specific cases where this is possible. Sometimes it's not really easy to come up with a common base, or it's not really possible because it might be like a real messy decimal, or like not a whole number. So it's not like something you'd really be able to recognize by looking at, or even with a calculator, it would be tough to figure out exact values. So let's look at how we can solve problems if this isn't the case. I mean, you should always, like, if you notice you can do it with a common base, it's always fair game. Like, usually this might be easier to do, especially if you didn't have a calculator that can do logarithms. But realistically, this method only works in special cases like this common base. So how do we solve an example like number 3? Like, we have 2 up to a power equals 61. There's no way I can write this as 2 up to a power. Like, 2 up to what power is going to be 61? Like, I mean, you could get close, but there's no like whole numbers. It's not like it's 2 up to the 6th or 2 up to the 5th or something. Like, it would probably be like a decimal. And so it's not, one, it's going to be hard to get the exact value, and it's not easy to figure that out really quickly. So how we can do this is, the first thing you want to do is make sure your exponential expression is isolated, which in this problem it already is. Like, we don't have anything added or multiplied to that. But how you deal with this is you take the log of both sides. So I'm just going to write, but like, you basically have log of 2 to the x equals log of 61. So like, we're going to see basically when you get a situation like this, if you take the log of both sides, because we're doing it to both sides, so that's a-okay. It's just like if you add 1 to both sides in an equation, that's okay. You're doing the same thing to both sides. So we're not changing the problem necessarily. So if you remember like some of our log rules, remember, if you have a power, you can pull that x to be in the front. So you'd really have x log 2 equals log 61. So then the solve for x, this is really multiplication, so you would just divide that log 2 to the other side. And then you're just going to want to put this in your calculator. So you're definitely going to want like a scientific calculator. You could use something on your phone, or if you got a graphing calculator, or just any calculator. You should see most calculators have a log button, at least most like scientific calculators. So you don't even need like a TI-83 necessarily. But if you just type in log 61 divided by log 2, you're going to get a decimal. It's approximately 5.93. So see, like we tried to write this as a base, like it would be 2 up to the 5.93 would equal the other side. That's not something you're just going to look at and be like, oh, it's obviously the common base. It's 2 up to the 5.93. You know, I mean, that's not an easy thing to see. Oops, I didn't mean to erase. So that would be our answer. And you can get extraneous solutions. It's not really anything crazy. I mean, you could just plug it in just to see. I'm trying to think where you would really get extraneous solutions. Well, we'll see how that comes up with problems like these. So what was I going to say? There's something I was thinking. If I think that, I'll make sure I say it. Similar idea for question 4, like your exponential part is already isolated. So you'd have log of 8m minus 7 equals log of 92. So you can bring your power to be in the front. And if you want to do like this step, like especially when you're getting better at these, you can probably start doing multiple steps at the same time. But basically you're gonna just divide that log 8 to the other side. So we just have m minus 7 left on that side. So we'll just put this in our calculator. So log of 92 divided by log of 8. And you should get roughly 2.17 if you just kind of round it a couple places. And then we want to add that 7 over. So like our final answer would be 9.17. One thing I remember what I wanted to say, so sorry. When you put these in your calculator, make sure you close your parentheses. Like when you type in your calculator, make sure you close this parentheses before you divide. Like if you're doing in problem 3, make sure you close your parentheses, because if you don't, it's going to think you're just dividing the 61 instead of that log by it. So make sure you close your parentheses when you're typing these in. That if you got a different answer than I did so far, that's probably what you did. So that's pretty much the really the big idea with these. You just want to make sure you isolate your exponential part. So maybe I'll do 5 and have you try 6. But like in number 5, so before I take the log of both sides, I got to get rid of this 4 in front. You want to just make sure like what you have up to your exponent, like your base and your exponent is isolated. So if you've got extra stuff multiplied or added or subtracted or whatever it might be, you need to get rid of that extra stuff before you take the log of both sides. So like in this problem, you would divide the 4 over first. So 148 divided by 4, that's 37. And now you would take the log of both sides. So, I mean, remember, you can pull the power to be in front. And then you're just going to divide that log part over to get your variable by itself. And that's pretty much how these go. I mean, depending on how much you have in your exponent, if you've got extra stuff, it can get a little bit more steps once you kind of do this. But I mean, pretty much these are going to be pretty similar for pretty much most of these problems you see. I mean, there's things they can do to make you have extra steps or things, but it's approximately 1.86 if you round a little bit. And so how about you guys try number 6? And while you're doing that, I'm gonna double check the key. I want to make sure that none of these, how many of these are extraneous, because so far I don't see where any of these haven't worked. So like looking at number 6, like the first thing you want to do, like you want to get like your exponential part by itself, like your base up to the power you want to get by itself. So like the first thing you want to do is deal with this -5. Like that's like kind of like extra stuff on that side. So I mean, you would just add the 5. That would be your first step. So then when you have your base or a number up to like your power, now you're going to take the log of both sides. Usually I just kind of write it, like try and squeeze it in, but that'd be log of 8 then on that side. So once you get to this part here, remember one of our, it's called the power, I call it the power rule, but when you have an exponent with a log, remember you can pull that to be in front of your logarithm. So like that 3w would be in front times your log of 4 equals log of 8. And now we want to just get our variable by itself. So this w. So I mean, we're going to divide. I mean, really, you're going to divide by the 3 and the log base 4. So if you want to do it all at once or one step at a time, maybe I'll just do one at a time. But you really could, to save a little bit of time, you could do log base 8 divided by 3 log base 4. Not base, log of 4. But if you did this, you'd have 3w equals log of 8 divided by log of 4. And like I said, when you're plugging in your calculator, make sure you're closing your parentheses, but that is 1.5 exactly, like not even rounding. So then if you divide by 3, you're just going to get 0.5. And please don't be afraid to ask like questions. I mean, I know this is probably a little bit weird. But once you get like once you kind of see the steps we're doing, I mean, it's pretty similar. But basically why this works too is like when you take the log of both sides, it just, and it doesn't, I mean, we're just using the regular log. I mean, technically you could do a log of any base. Like if you did, we just do log base 10 because that's what your calculator can plug in easily. Let me know if there's any questions before we move on. I want to make sure that I'm not. But it's really not that bad. I mean, really the only thing that can really make these problems kind of stink is one, if you've got a lot of junk to deal with first, but it really depends how complicated your actual exponent is, because you might have extra steps when you're solving, or if you had like a quadratic, if you had like a w squared, like a w squared or something, like a power and a power kind of thing, like it could get a little bit more steps when you finish your process. But I mean, realistically, it shouldn't be anything crazy. And we're going to see why this is a nice thing. If you remember, like when we looked at like some of those word problems from before, like usually we would just kind of plug it into that formula. But if you wanted to solve for like an exponent, for example, like which usually represented time in those problems, like you can use this to figure out how long it would take something to reach, like if you were looking at a population question like that grew at like 10% every year, like how long would it take to reach this population? You could calculate for your variable instead of like your variable and an exponent instead of just like a regular variable that we're used to solving for. Question 7, I mean, pretty much the same idea. You'd want to subtract the 7. So you'd have negative 4x plus 1 equals 11. This one's a little bit, we got to be a little bit careful with this negative. Like it's not included in what's being raised to a power. Like if they wrote it like this, but you're going to actually want to get rid of this negative 1 that's times this exponent part. It's not like the negative 1's not actually being raised to the power, if that makes sense. So you'd also want to divide by negative 1. Like if they had written it like if it was inside your parentheses up to that power, but that negative is not included. Like only the 4 is being raised to the x plus 1, if that makes sense. Like I know like how it's written, sometimes it's like if they would make it real clear if that negative is included by putting parentheses around it. But we would get 4 up to the x plus 1 equals negative 11. So to solve this, we would take the log of both sides. But we're going to see this is a problem. Because if you remember, I mean, I don't know if I did the greatest job yesterday, but if you have a log of a negative number, that's not okay. That's undefined. So if you ever are solving these exponential equations and you get a log of a negative number, you can just stop. It's going to be no solution because of this. You can't, remember, you can't have a log of 0. That's not okay. And you can't have a log of a negative number. not okay. You can only have a log of a positive number. Like that's the only thing that's good. And the reason why is, remember, like what a log tells you, like if you have a log of, say, like why this is a problem. Like remember, this is base 10. Like 10 up to what power is going to equal -3? You could try as long as you want. You're never going to, no power will ever give you a negative number there, because positives is just going to make it get bigger. A 0 exponent would equal +1. A negative exponent, remember, just flips it over like a fraction. So like 10 up to the -2 would actually be 1/100. It wouldn't be a negative result. So there's no powers that work. So if you're ever solving a problem, or if you plug in an answer and it gives you a negative log, like that's an extraneous solution or it just doesn't work. So that's what you really want to be like in terms, like when it's talking about extraneous solutions in these steps, that's really all you're going to be checking for. So I'm trying to think. I'll might skip. Let me look at some of these later ones if they get more. Too. I mean, they're pretty much, like I said. I mean, there's nothing too crazy going on. I mean, like, let me just double check the key just to make sure I'm not like overlooking something. So maybe I'll just do a couple more. I mean, I can do them all. I just feel like it might be a little redundant. Or if you guys want to try some of these, I mean, or if you even want to go into your Delta Math, maybe I should look at the Delta Math and tell you some things about that. But if you want to start working on that tomorrow, yeah, I'm going to skip that one. Let's go to one of these bottom ones because it looks like maybe they got a teeny bit more going on in the exponent. But like a problem like 13, remember, you want to get what your base up to the power by itself. So we got to deal with that 6 in front, and we got to deal with that -2 in the end. So you always want to add the 2 first. So you have 6 times this. And then you would divide that 6 out. Kind of like, basically, if this was like an x, if you had 6x minus 2, you would add the 2 over first, then you would divide by the 6. Like if you kind of just treat it like it was a basic equation. So you would get 16 up to this. 84 divided by 6 is 14. So then you would take the log of both sides. So you can bring that in front. And I mean, you would just kind of solve this. There's kind of a lot going on. I mean, the first thing you want to do is just divide this log part to the other side. So log of 14 divided by log of 16. So it's approximately 0.95. And honestly, usually I don't round, I just keep this in my calculator, like this 0.9518387,305. Like I keep it in my calculator and then I just solve from there. So I would subtract the 2. So I mean, it's approximately like -1.04 or 5 if I round it, actually round up. Then divide by 7. So it'd be approximately -0.15, if you round a little bit. But I try not to, like when I do these in my calculator, I try not to round until the very end. Like I try and keep it in my calculator the whole time, like the whole decimal. Just because, like, I mean, by rounding early, you could get a slightly different end result. So if you're really trying to be precise, you don't want to round early on in the problem. You want to wait till the very end if you're going to round at all. If that makes sense. I don't know if that makes sense, but like I keep like the whole thing in my calculator when I'm doing this. I don't like type in 0.95. I'm just writing at what I have. I mean, it would be like ... I rounded it when I wrote it here, but like I didn't actually in my calculator. So I'm gonna